1, 2. Okay, then now the record is on. So we're just gonna jump into the first example. This is the investigation of your beam now. Okay, now this is a very good example that I have had in my class. Says that okay, this is your beam. Okay, and it has a bracing here and here. And to consider something a bracing, it's like this. As I've mentioned before, bracing, it is something that can prevent either lateral or torsional movement of your beam. Remember, the most important thing is that lateral torsional buckling, both deformation have to occur simultaneously. I mean, at the same time. So if you can prevent either one of them, maybe prevent your beam from twisting or moving laterally, that becomes a brace point. Okay, maybe you can take a closer look at this. You see, these girders here, they are in the air, right? They are in the air, so they're gonna move laterally, but they put the brace on like this. So they're gonna move laterally all together without being able to twist. So these becomes bracing because the girders cannot twist. They're just gonna move to the side together. See, they got a truss over there, all over the place. That's a bracing. Okay, so see, even though the beam itself is very, 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 very long, but we design this beam based on this unbraced length only. Okay, and if you consider this beam, perhaps you see this beam, the secondary beam that comes in, is going to come and brace the beam there, come and brace the beam there, come and brace the beam there, and brace the beam there. So when you design it, that becomes your unbraced length. Okay, and in similar fashion, see that beam will have this as the bracing as well. See, so that becomes your unbraced length. So many people will not understand that. Okay, and that is the most important thing. So now we're back here at our example. Okay, so now we have the bracing like this. So we can skip this part very quickly, you know, shear force diagram, bending moment diagram. Now, if this is a bracing, it means that this is going to be your unbraced length. This is going to be your unbraced length, and that is going to be your unbraced length. So in designing this beam, you must consider 3 regions. Okay, that is a region number 1, region number 2, and region number 3. Okay, so that will be very interesting. Okay, I have it here. So let's emphasize this a little bit. That's your region 1. Okay, that's your bending moment diagram in region 1. That's a region 2. And then say this is your region 3. Each has its own bending moment diagram and unbraced length. Now it's interesting because I love this example very much because it contains everything. Wow, it's a very well designed example. The first region, unbraced length is short. You see, unbraced length is short. And when you have the section, now it's H450 by 200 by 66.6, you can take this information out. So this beam, if you cannot see the picture, what is this? Okay. 450 by 200 by 66. So it's It's this one, right? Oops. So you see what you can have from here is a LP and LR. Okay. So now you take this out of the table. You go back and look at this. That's LP and LR. So the first region, see LB unbraced length is less than lambda P. So in the first region here, you're going to reach MP, right? Are you still with me? Hello?
Yes, yes.
MP in this region because LB is less than LP. So we don't need to consider CB because you already reached MP, correct? And that means for region 1, the calculation is going to be straightforward. In region 2, look at the gradient moment. You see, this is when you have the positive moment and negative moment, correct? So your mechanics of material and structural analysis would tell you that your bending moment will have the point of inflection, or we shall say double curvature. Correct? So imagine this, the beam with the double curvature like this, positive moment and then negative moment. This beam will be very, very difficult to buckle because the portion itself is already under the double curvature. So it just like has its own extra stiffness. Because of this double curvature, it means that your CB is going to be very high. But this region number 2 still has the maximum moment there. When you consider this, you must consider this. Region number 2 with its own CB and the maximum moment that lies within that region. Okay. Now, region number 3. See, CB is going to be equal to 1 because that's a cantilever without bracing. So you have low CB, but then moment here is not large either. So it's kind of difficult to tell right away what's going to happen. Now, this is the big picture that you need to investigate before you start your laborious calculation. Okay, so now we have the big picture. Region 1, oh, I already have everything for you. Region 1, M is maximum, but unbraced length, lambda LB is less than LP. So don't bother. You see, highly unlikely to govern. We can make that statement. Okay, but you can still go ahead and do it. LB is less than LP, CB doesn't apply, and we have you can take note that this is plastic behavior because you reach MP. M nominal is going to be MP. Okay, and you can take this from the table or you can just calculate. And this is LRD again, 0.9 to 2500. Oh, we are using the SM520, right? Oh, SS400. So yeah, and the plastic section modulus, you can take that from here. It's a 1450. Divided by 10 to the power of 5. Okay. In region number 2, it's going to be very interesting. Okay. Now your LB is 5 meters. Clearly is beyond, way beyond LP, but not beyond LR. So this is inelastic. Okay. You define the behavior here. Okay. You can use this formula simply because your unbraced length is, say, greater than LP, but still less than LR. So it's inelastic. As soon as we don't have the plastic, we get the help from CB. So to calculate this CB here, you need to take the bending moment diagram of that region. Okay, considered region. Okay, this is region 2 bending moment diagram. The M max is this one. That's the maximum value. And then we divide this into 4 quarters equally and calculate our bending moment values here at each quarter point. So go back to this. M max is 29.4, right? That's your M max. That's M max. And then MA is going to be 16.5, MB 3.48, and MC, even though it's negative, but say we use only absolute value. So you see, you even have the example here to show that, okay, we only care about absolute value, you see. And we got 2.22 for CB. It's like 100% increase, you know. 120% increase because of the double curvature. So even though, yeah, that's the inelastic calculation, right? And say I pick MP and MR out of the table. So that's MP minus MR. That's LB minus LP, and then LR minus LP. So out of this, without CB, you get only 24.5 ton meter for your design moment. And compare this to your VMP, that's 32.6. So it's down. This is your full value, right? 32.6 is as much as you can get. Okay, that's the biggest one you can get because that's MP. Now, without the help of CB, you get 24.5. But the fact that you have a double curvature, so CB bumps up this value to way beyond MP, you see? So you can see that this is greater than MP. Bad handwriting. Oops, that's even worse. Okay, greater than, because the fee is already included, so it's greater than fee MP. So you are down to MP. Then therefore, in the end, VMN is equal to VMP, 32.6, which is greater than the maximum moment. So we are okay, just like this, the first region. So you see the second region, even though the unbraced length is way longer than the first one, but CB helps increase the design moment into exactly the same as region 1. All right. So then we move on to region number 3 here. Again, LB is greater than LP because I believe we have 3 meters. So this LB exceeds limit LP, but not by much. And we are not going to get help from CB this time. So, okay. Oops, sorry. Now, use of CB is not allowed in this cantilever with no end bracing. So it's just this calculation, but change your LB into 3 meters. So it's only, you know, exceeds the limit LP a little, okay? CB is equal to 1. So we have a slightly down number from VMP, which is 32.6. So now we have only 30.2, but still it is greater than the moment in that region. So we are still okay. I went ahead and performed the shear analysis as well. The H over TW ratio is less than 70. So I got VN, still fine. Okay. So then that's it. And yeah, I believe that I have the local buckling check here as well in the beginning. So what is that a question?
Excuse me, for the region number 2, why the equation will rewrite for 2.5 M max plus MA, MB, and MC? Because the equation in the lecture you write is 3 MA plus 4 MB and plus 3.
Oh yeah, you're right. I never noticed that. Yeah, yeah, I missed it. Copy and paste problem. Thanks a lot. That's 3, 4, and 3 missing. Thank you very much. Guess what? The answer is the same.
Okay, okay.
All right, thanks a lot. You are very concentrated, very admirable. Okay, is there any more question? All right, folks. More example, and then we're done. Now, notice that we have the same problem when it comes down to design, just like the compression member. Because if the unbraced length becomes the issue, how can you pick up the beam? Right? So that's why I have this table for you. Okay? You now have table C and table D where you have, okay, for the unbraced length, say 2 meters, this will be the flexural capacity of every section when the unbraced length is 2 meters. And when the unbraced length is 3 meters, you're going to have this. Okay, and I have a lot more in the table. Okay, but the table is not here in the iPad, it's in the computer. And I'm afraid of swapping that back to computer. I may lose connection. But I have posted this table for you guys, and you should be able to see this. Okay, so when you face a situation like this, okay, now, wow, what's going to happen? This is our beam. So how are you going to design this one? Okay, for example, in your project, you have your beam, say 4.5 meters long, right? Then you're going to have your uniform load. Okay. Now, you know, your CB is going to help somewhat, right? So we can also take CB into our consideration to help our design value as well. I thought I had it with me, but I don't. Just looking again at the same thing in the morning. Okay, well, I don't, that's fine. Maybe I could some of this. Okay, well, I don't, and then I don't. So like this, for your project, when you calculate, let's say we're going to use ASD, okay? Now you're going to have your MA equal to, let's move it here. Your MA is again WL squared over 8, right? And let's say, because this 2 meters is, okay, your project first. 4.5 meters is pretty long. And now you know you're going to have to enter the table with LB equal to 4.5. And chances are your beam is going to be, you know, it's not going to be able to reach MP. So before you enter the table, you may enter the table with the value of MA divided by CB. Okay, but now don't forget that you got to have to include factor of safety somewhere too, because this moves from the nominal side. And then this guy cannot be greater than the nominal moment. So that's how you can pick up the beam. So you may notice that I also have this column here, maximum CB. So what does it mean? It means that when you consider this beam, 80 CB beyond 1.11 will shoot this beyond MP. Okay, remember our design curve looks like this, and then the CB will bring this portion up. Okay, so let's say if you pick up this beam for your design and 2 meters, this is not MP, but it's very close to MP that the room for CB is only 1.11. As soon as your CB exceeds 1.11, the value that you are going to have will multiply with this. You're going to exceed your MP. Okay? Do you understand that? In other words, let's say if you calculate and you get the CB value greater than this, you know you're going to get MP. These numbers are based on CB equal to 1 as well. So that when you enter the table, you can divide your calculated moment by CB. And actually, oh, as you know, that's a fatal error. This has to be like this, right? Because it's MN divided by factor of safety, it's ASD. Okay. So what do I do with this case? I think I'm just gonna have to go on and say, try to pick up this beam. Let's say, when you look at this beam, what do you need to do? The analysis has to be done, right? And so, oops, my MA would have to be equal to how much? Can you help me calculate this? The maximum moment at midspan, the easiest way just to do the direct analysis. So the reaction here is 12,000. So the maximum moment here is 12,000 multiplied by 5 minus 8,000 multiplied by 3, right? So that's 60. Am I correct? I am correct, right? And this is our beam. I have M max here. Okay. And this value is not of my concern because let's say this is 24. So we have 2 regions, so to speak, right? This is my region number 1, and this is my region number 2. Look at my region number 1. Now that I know, let's say this point load will become my brace point as well, somewhat. If it's not, it's going to be a different story. But let's say I try to look for the root of this. Okay, brace points are at each concentrated level. Okay, location. So that means at region number 1, you see, I can recognize right away that this is the triangle. So I now know that CB here is 1.67 right away. And my M max here is only 24,000 kilogram meter. And my unbraced length is 2 meters. So you see, by inspection, this portion is not going to govern my design. Right? So I move on, let's say, by inspection. This will not govern. So we move on. I have plenty of space. Why do I just have to clamp everything down there? So let's move here. Let's move everything down here. Okay. Region 2 now. Oh, okay. Very well. I thought I would have another page. Okay. So region 2. Are you with me? It's all been very quiet.
Yes.
Okay. Region 2 now, it should be the one that we consider to design this B. Okay. So now I have to perform CB calculation. And now, wow, I don't have anything with me, so it's going to take a while. Must have lost it somewhere. Okay. So that becomes my moment. Okay. If that's 24, let's say 10 meter. Okay. Too tired of writing a lot. That's 36 10 meter. Now I have to break this into 3 equal lengths. Okay. It's that's 30, right? That's 27. That's 33. Okay, so can anybody help me, please? I don't even have a calculator around. So CB is going to be 12.5 M max. That's 36. 2.5, 36 plus 3, 27 plus 4, 30 plus 3, 33. That's going to be our CB. Okay. How much is that?
The value is 1.33.
Oh, 1.33.
Yes.
Thanks a lot. So, okay, now we can, unbraced length is, CB is now 1.33. M max is 36,000 kilogram.
Sorry. Sorry. The value should be 1.15.
Yeah. So it's close to a uniform load. Is it?
Yes.
Can anybody double check? Or quiet. Anyway, let's believe that. Okay. Unbraced length is 3 meters. So now we can enter the table with moment MA equal to this divided by 1.15. How much is that? Please.
31,304. 304. Or you can use this value. Is okay.
Come on. Okay. So we know this. So unbraced length is 3 meters is here. And we are looking for 31 something. Right? That's the number that we are looking for because we got the help from CB. So look at what we have here. Beautiful. Saw something here. And see, our CB is less than the maximum value as well. So we're going to get the value. Okay. I think this should give us a pass. Okay. Or can we look for something better? The next, say, good section. That one is also good. You see that? Greater value, CB, this exceed, and this one is deeper and lighter. Considering that, okay, that is also applicable, right? Another one that would work is going to be perhaps this one, because the moment is greater, but CB now, you know, you're going to reach MP here. That one. So out of these three, okay, down here is going to be quite huge. Another one that is close will be this one. No, I don't see any. It's 30 something, right? So that one is too large already. So out of these three, which one would you like to choose? All quiet. I would go for this one definitely if I don't have the depth limitation, right? The deeper the better. And see now it's slightly less than that one as well in terms of the weight, and I have more domino moment due to say depth. So if depth is not an objection, I would use this one, and of course it would have the greater moment of inertia to deal with deflection as well if need be. Okay, so now you can select that, and you're just gonna have to now try this section and investigate it the way we did before. Okay, you can do it yourself, right? Hopefully. So it's just going to be exactly the same as, say, this. Okay, for region number 2, now you have your CB, investigate everything. It's just the example for selecting your B. That's all. Any question? Where did I get this B? And how come I don't have any calculation? I must have it somewhere in the office. It surprised me a little bit. Anyway, any question?
Can I ask the question for the author example, or you would like to ask for this one first for author?
Another example in this session?
Yeah.
Of course, of course, of course, of course.
Example 15. Okay. I just wondered why the shear force diagram will have this value since we didn't have any loading on the structure.
Oh,
or
yeah.
how we
Oh, you know what? Yeah, it must have. And you instead of asking for that, I missed the load somehow.
Okay.
Sorry, yeah. All right. 30 tons here. Oops. We shouldn't have moment. We don't have a load, right? We shouldn't have anything. That's 7.5 tons. Is that some kind of glitch? Let me check this. Funny how. Thanks a lot. So you found 2 grave mistakes here, right? What's another one? Right, so there's no load on the original word file as well. It's like just it went missing. It's like that. Hey, thanks. I'll fix this. Okay.
Yeah. And the basing when we add is it behavioralize a support, right? As you can see.
The support sometimes is not a bracing, but most of the time it should do the job. But it say if you place the beam on concrete, it may, let's say if you have this example, okay. Remember this one from last week? Place the beam on the support like that. Say this is on the base plate, right? And the base plate is welded to the beam, and then the base plate itself is connected to the concrete by the means of the anchor bolts. So to say that this will be strong enough to provide the bracing, we perhaps need to check whether or not the anchor bolts can sustain the force generated by the need of the beam to move as well. Good point, but generally it should be enough to prevent the lateral torsional buckling. Yeah.
Could you turn down a little bit for the check of the deflection after I review for the video?
This
Please
one?
go up. Yeah. After we calculate for the deflection, we got to 0.1 centimeter, right?
Yeah.
Which is should be lower, right? Should be lower from the limit.
Okay. Yeah, I always have trouble with this.
Of course.
Thank you.
I had to think again. If you mentioned for the video and I misunderstand or not, yeah, it's okay.
Yeah, I didn't even notice that.
Of course.
Thanks a lot. Okay. Wow. I better fix it now, now that I'm at it, before I forget again. See that? It's always like that, right? Human.
And for the check of the criteria of the deflection, we're gonna use this equation all the time, right? 5 divided by 384 and time the term.
Well, this is what. Why do you ask that? This is the formula for the deflection due to a uniform load. If it's not uniform load, you use it.
Yeah. Okay.
That's not a good question, but it's a question that you need to ask anyway. Okay, it's better to ask. It's still better to ask than not to. But you should know the answer. Okay.
I like it for the structural analysis number 1, right?
Yeah. No, actually, you learned that in mechanics of materials, right?
Oh.
Calculation
Okay,
deflection.
okay. Yeah.
Okay. So, is there any more question? I'm fixing the file now as we speak, because if I don't do this, I will never do it. Okay. Could you spend a few minutes looking at the design phase 5 about the base plate and see if you have any question about it, because I think it's straightforward. And maybe I'd like to wrap it up today so that you're free tomorrow. You and I are free tomorrow.
That means for the phase number 5, we need to make sure that our calculation of the load from the column will correct first, right?
Yeah. If it should be correct, right?
Yeah. Yes.
Shouldn't be that.
So I would like to ask TA.
Yeah, sure. So you just, I think, has she returned the graded phase 3? Oh no, not yet. Oh, it's phase 4, right? Yeah. But
yeah,
it should be straightforward. And in fact, I asked you to submit the load for review. So,
yes.
you have it correct, right?
Yes.
You should. And, let me talk a little bit about it, because I think it's better than reading. Okay. Okay, so let's here. It just no big deal, because now you must have the phase 5. Now you have 2 columns, right? from phase number 4, you have 2 columns. So sections or sizes. Now you use them to design the base plate, but make sure that first, say, the plate will have to be slightly bigger than your column, right? You know, the first batch that we used the design project as the homework, most of the class mess up. Plate size larger than column footprint. Because you need to weld the column to the base plate, right? You need to weld them like this. In order to be able to do the welding, it has to be bigger. It doesn't matter if your required area is less, but you have to use the bigger physical size. Otherwise, it's impossible to do the real job. Okay, and now you have the it means that if you calculate and the size of the base plate is already smaller than the column footprint, the concrete crushing should not be a problem. Okay, and now once you have the physical size, you just try to use practical size if possible. Practical is like this, right? Use practical size as well. Keep it square if it's possible. And then once you have the practical size, because you understand that in one hand, you will have the calculated value, right? For example, you need this size, but in the other hand, your calculated value is not the one that you should use because of, you know, the construction and fabrication reasons and so on and so forth. So make it practical, and once you have the practical size, which of course should cover the need from concrete crushing, then you can calculate the maximum value for M and N, right? You cantilever distance on either side, and then use that distance to calculate your plate thickness. Okay, but don't forget that the FP for your plate is going to be equal to the load from the column divided by the area of the plate. One more thing, a common mistake is that the FP plate design here use actual load, not concrete crushing capacity of your abutment. Okay, because sometimes, okay, you got the load from the column, you design the size of the base plate, and then you would calculate the concrete crushing strength to compare with the load that your concrete has to carry. And then many students will end up using the concrete crushing load to design the base plate. No, you use the load that your column has to carry. That's a real load that we aim for, right? But these are the common mistakes made before. That's why I want to talk a little bit about it to prevent you from making those mistakes again. It's written in the design phase 5 already, but I think it's better to give a talk as well, go along with it. Okay, so is there any question?
In practical, when we're gonna weld for the base plate, it's gonna like a braille, not bolt anymore, right?
No, how can you attach the base plate to the column? Right?
Yeah. Oh, yeah. It does not have any plan to attach. Yeah. I see.
Mm-hmm. So when you have the base plate at the end, you can just say use the bolt to adjust the leveling of the column during erection.
Like anchor, right?
Yeah, anchor bolt, exactly.
Yeah. Okay.
Okay.
That means the anchor bolts will apply for the lower part of the column. So that means it must have
No,
the
the
strength.
anchor bolt will apply like this. We have pictures, I believe, but it's in chapter 4. Here, like that. And generally, this anchor bolt should be in concrete first, you know. So they're waiting for the column and the base plate to come in. And you would have the concrete here like this, abutment, right?
Yes.
And when it comes in, when you're done adjusting that, generally there should be a gap left, and we are going to put the high strength grout here to fill the gap. Column base plate in the end is gonna look something like that.
Oh, I see. Okay.
Good. Is there anything about this piece of cake, you know? Very simple. Okay. Maybe go back here. So is there any question? Let's pause and wait for the question.